A small machine rests inside a metal cylinder colder than interstellar space. It does not look like a doorway. It does not look like a telescope. It does not even look like a machine that could trouble the foundations of physics. Yet a processor no larger than a coin can finish a carefully designed quantum task in a few minutes. While the best classical computers would require a span of time so long that ordinary comparison begins to fail, the shock is not only speed, speed is the visible part. The deeper question is stranger and quieter. What physical resource is being used when a quantum computer works? A classical computer moves through information by arranging bits into definite states. Each bit is either 0 or 1. Each operation changes definite symbols according to definite rules. The world of ordinary computation is a world of decisions already made. A quantum computer does not begin there. Its basic units can hold possibilities together before a final answer is forced into view. That sounds like a technical difference. It is more than that. It changes what computation means. At first glance, this may seem like another story about a faster technology. It is not. The machine is fast because it relies on a layer of nature that does not behave like the layer that chairs, clocks, and handwritten notes appear to occupy. What seems solid at human scale becomes conditional at smaller scale. What seems separate can behave as one. What seems decided can remain open until an interaction makes it part of the shared world. The stake is clear. If these machines keep improving, they will not only solve certain problems faster, they will force the old picture of reality to make room for something it was never built to contain. The first useful image is simple. Imagine a silent library at night. A classical machine searches one aisle after another, even if it does so with enormous discipline and speed. A quantum machine does not search the library in the same way. It prepares a pattern where many possible routes can interfere, cancel, reinforce, and leave behind a final result. The answer does not come from checking every shelf. It comes from shaping the whole pattern so that wrong paths fade and useful paths remain. That is the promise. It is also the problem. Where does that pattern exist while the calculation is running? This question should be handled carefully. A quantum computer is not proof that parallel universes are physically real. It does not settle the oldest arguments in quantum theory, but it does make those arguments harder to ignore. Some interpretations describe the calculation as spreading across many branches of reality. Others describe it as information evolving in a single quantum state. Others say the wave function reflects knowledge, not a physical object. The measured result is the same in each case. The story underneath is not. That gap matters. The chip works. The explanation is still contested. It is worth pausing there. Modern science usually feels most secure when a machine and its meaning arrive together. Build a radio and electromagnetism explains the waves. Build a refrigerator. And thermodynamics explains the flow of heat. Quantum computers are different. The rules that predict their behavior are extraordinarily accurate, but the physical meaning of those rules remains disputed. The engineering is becoming practical while the deepest interpretation remains unfinished. That is a rare situation. It is not failure. It is tension. A calm journey through that tension begins with one question. When a quantum computer produces an answer that no classical computer can realistically obtain, what exactly has done the work A-like on this kind of slow science journey simply helps more quiet, careful explanations find the people who enjoy them. The thought can then return to the machine itself. It waits in darkness, shielded from heat, vibration, stray radiation, and almost every touch of the surrounding world. Its strength depends on isolation. Its usefulness depends on control. This is the first paradox. The device must be separate from the world while computing, then joined to the world when read. Too much contact destroys the quantum state. Too little contact makes the answer inaccessible. The difficult thing is not making the strange state. It is keeping it alive long enough to matter. Human intuition reaches its first boundary here. At everyday scale, observation seems passive. A mountain is not changed by being seen from a valley. A cup does not decide its position when light reaches the eye. But a quantum system is not a tiny version of a cup. Its possible outcomes are not always waiting like coins under cloth. The act of extracting an answer helps determine what becomes definite. This is why a quantum computer is both a calculating device and a disciplined negotiation with measurement. If the central paradox had to be answered in one line, which option feels most plausible? Hidden worlds, hidden information, or a reality that only becomes definite through interaction? The question is not a poll of belief. It is a way to feel the shape of the problem. The coming path clarifies the pieces without forcing a premature conclusion. First, ordinary computation reaches a wall because some problems grow faster than any machine can chase. Then a qubit appears not as a magical bit, but as a physical system that can preserve multiple possibilities in one fragile state. From there, many qubits create a space of states so aerial that classical description becomes impractical. Entanglement then removes the comfort of separateness. Decoherence explains why this strangeness usually disappears from daily life. Error correction shows how engineers keep it from disappearing too soon. Each layer changes the meaning of the one before it. The result is not a loud mystery, it is a precise one. A cold chip in a laboratory does not need to look dramatic to change the question. It only needs to work. And because it works, the problem can no longer stay in the margins of theory. The first step is to understand why ordinary machines, no matter how powerful, meet a limit that quantum machines approach from another direction. The wall faced by ordinary computation is not caused by laziness, poor design, or a lack of imagination. It is caused by growth. A classical computer can be made faster. It can be given more memory. It can be connected to other machines and arranged into a vast system. But for certain tasks, every improvement is swallowed by a simple mathematical fact. Each added choice can double the number of possible paths. Doubling feels harmless at first, then it becomes a cliff. It is useful to imagine a small maze drawn on paper. At the entrance, there are 2 possible corridors. A patient person can try one path, then the other. Add a second fork and there are 4 possible routes. Add a third and there are 8. For a while, the growth still feels manageable. The maze remains a puzzle, not a universe. But after many forks, the routes multiply beyond any ordinary sense of size. The difficulty is not walking a path. The difficulty is that the number of paths grows faster than the world can provide walkers. This is the first scale that matters. A problem with 10 binary choices has a little more than 1,000 possible states. That is easy for a laptop to handle. A problem with 100 choices has more possibilities than a human mind can picture. A problem with several hundred choices can outgrow the number of particles available in any practical machine. The number is not the main shock. The growth pattern is. Classical machines operate by storing and updating definite states, even when many processors work together. Each one is still handling definite arrangements of bits. The machine may divide the labor. It may be extraordinarily efficient, but it must still represent the relevant possibilities in some physical way. Information is never free. It needs memory, energy, time, and structure. That requirement becomes severe when the problem is quantum. A classical computer trying to simulate a quantum system must track many possible states at once. For a few particles, this is possible. For many particles, the description expands with brutal speed. The simulation becomes like trying to draw every ripple in an ocean by assigning 1 clerk to each curve of water. At first, the office functions. Soon the building's too small, then the city is too small. Eventually there is no meaningful place to put the clerks. This corrects a common false intuition. The issue is not that classical computers are stupid and quantum computers are clever. A classical computer is one of the most precise tools ever built. It is superb at tasks that fit its structure. The problem is that nature itself at small scales is not arranged like a list of definite yes or no entries waiting to be checked. When a classical machine simulates that nature, it has to translate a quantum process into classical bookkeeping. The bookkeeping is what explodes. The map becomes larger than the country. A quantum computer begins from a different position. Its hardware is already quantum. It does not need to translate every part of a quantum state into a classical list before using it. It can let physical possibilities evolve together inside a controlled system. This does not mean it tries every answer like a magical army of machines. That image is tempting but too simple. A quantum computer must be arranged so that its possibilities interfere in a useful way. Most possible paths are not answers. They are raw material for a pattern. Interference is the quiet engine. When waves meet, they can strengthen each other or cancel each other. The same basic idea appears in water, sound, and light. In quantum computation, the waves are not waves on a pond. They are amplitudes, which are numbers that describe the weight and phase of possible outcomes. An amplitude is not a probability yet. It becomes part of a probability only when measurement brings an answer into the classical world. This matters because a quantum algorithm is not just a search, it is a choreography of amplitudes. The machine tries to make wrong answers, cancel, and useful answers survive. A calm physical image helps. Picture a dark hall filled with many faint tones. Some tones arrive out of step and disappear into silence. Others arrive aligned and become audible. The final note is not produced by one singer alone. It is produced by the relation among all the tones. In a quantum computer, the answer emerges from relations among possible states. The visible output is small. The hidden coordination is vast. This is where human intuition reaches another limit. Ordinary experience teaches that only actual things have effects. A door either opens or stays closed. A stone is either here or there. A written digit is either one symbol or another. Quantum theory does not preserve that comfort. Before measurement possibilities can influence later outcomes through interference. A possibility that never appears as the final result can still help shape what does appear. That is physically strange, but it is not vague. It is measured through the success of experiments. It is built into the operation of the machine. The foundation can now be stated more clearly. Classical computation is powerful when a problem can be reduced to a manageable sequence of definite steps. Quantum computation becomes powerful when a problem can be encoded into a quantum system whose possible states interfere toward a useful answer. The contrast is not between slow and fast in the usual sense. It is between two kinds of physical representation. One stores definite symbols. The other preserves a controlled landscape of possibilities. The consequence is immediate. Not every problem becomes easier on a quantum computer. Many tasks gain no advantage at all. Writing a document, sorting a small list, or adding ordinary numbers does not need quantum behavior. The power appears only where the structure of the problem matches the structure of quantum evolution. This is why the field is both promising and limited. It is not a universal shortcut. It is a specific key for specific locks. That restraint makes the achievement more meaningful, not less. The machine does not violate mathematics. It finds a place where the old method was using the wrong kind of tool. The maze was never meant to be walked corridor by corridor. It had to be turned into a wave pattern. Once that is understood, the next question becomes sharper. If the machine is not checking every path one after another, then the basic unit of the machine must be stranger than an ordinary bit. The route now narrows from the maze to the qubit itself, where the first real departure from common sense begins. A bit is easy to imagine because it behaves like a tiny decision already made. It is 0 or 1. It may sit in memory move through a processor or become part of a file, but its identity is definite. A qubit begins by breaking that comfort. It can be arranged so that 0 and 1 are both present in a single quantum state before measurement. This is often described as being in two states at once. The phrase is useful, but it is also dangerous. It can make the qubit sound like a blurred bit. It is not a blur, it is a physical state with structure. The common comparison is a coin spinning in the air. Before it lands, it seems neither heads nor tails, but a spinning coin is still a classical object. If every motion were known perfectly, the final face could in principle be predicted. The uncertainty belongs to the observer. With a qubit, that explanation fails. The missing answer is not merely hidden behind poor eyesight. The state before measurement is genuinely different from either final result. It carries relationships that a simple hidden value cannot carry. That is the correction intuition must accept. A qubit is not an ordinary bit wearing a mask. It is a different kind of physical object. In a superconducting quantum processor, a qubit may be built from a tiny circuit. The circuit is cooled until electrical resistance disappears. At that temperature, current can behave in a collective quantum way in certain designs. The system can hold two energy states as a combined state. The hardware is solid enough to be fabricated, wired, and tested. Yet the information inside it is not solid in the familiar sense. A metal loop can become the home of a possibility. This is the first mechanism beneath the calm exterior of the machine. A qubit has amplitudes. An amplitude describes how strongly a possible outcome participates in the state and how it is phased relative to other possibilities. One sentence is enough for the term. Amplitudes are the wave-like weights of quantum possibilities. If two possibilities are in step, their amplitudes can reinforce. If they are out of step, they can cancel. This matters because quantum computing uses those reinforcements and cancellations to shape the final answer. A classical bit cannot do that. It can switch. It cannot interfere with its own alternatives. The physical image is delicate. Imagine two quiet currents moving through the same narrow channel, not as two streams colliding, but as one pattern containing two directions of motion. The important thing is not that the currents are confused. The important thing is that their relation can be controlled. A pulse of microwave energy can rotate the qubit state. A neighboring qubit can be coupled to it. A sequence of operations can guide the pattern through a calculation. It sounds almost mechanical, but the mechanism lives at a level where ordinary pictures become unreliable. It works, but it refuses to look like anything simple. Measurement changes the story. When a qubit is measured, the delicate state gives a definite classical result. It is 0 or 1. The rich structure that existed before measurement is no longer directly available. This does not mean the earlier structure was unreal. If it were unreal, the interference effects would not appear. The calculation would fail. The qubit's hidden life matters precisely because it leaves measurable consequences after it vanishes from view. The consequence is severe. A quantum computer must keep qubits unmeasured while the calculation develops, yet it must also control them with extraordinary precision. Every useful operation is a careful touch that must not become a destructive touch. The machine has to ask the qubit to change it without asking it to confess. That is the narrow path. At human scale, this is almost impossible to feel. A lamp can be switched on without wondering whether the act of switching has destroyed the lamp's earlier identity. A page can be read without changing every word on it. But a qubit is not a page. The information it holds can be damaged by the wrong kind of contact, a little heat, a stray electromagnetic disturbance, or a coupling to the surrounding world can push the state toward an ordinary outcome too early. What appears stable depends on something fragile. The chip is therefore built like a sanctuary for controlled uncertainty. It is placed inside layers of shielding. It is cooled near absolute zero. It's connected to electronics that deliver pulses with strict timing. The goal is not to freeze the qubit into stillness. The goal is to let it evolve without being dragged into the classical world too soon. This is a less obvious point. Isolation alone is not enough. A perfectly isolated qubit would be useless because no operation could be performed and no result could be read. Full contact destroys the state. Full separation prevents computation. The useful region lies between them. The machine must be open to command and closed to disturbance. That balance is the beginning of quantum engineering. The qubit also changes what a physical state means. In classical thinking, a system state is a list of facts. Position, velocity, charge, temperature, and other properties can be imagined as entries in a ledger. Some may be unknown, but they are assumed to exist. A qubit resists that ledger. Before measurement, it does not possess a single classical value for the measured property. It possesses a state from which different values can emerge depending on how the measurement is made. The answer is not merely discovered, it is produced through interaction with a specific question. This is not philosophical decoration. It determines what algorithms are possible. A quantum algorithm arranges qubits so their amplitudes evolve toward a useful result. If the qubits secretly had ordinary definite values, all along the known advantages would disappear. The strange state is not an optional interpretation added afterward. It is the working material of the computer. The device computes with what common sense would prefer to ignore. A single qubit is already a challenge to intuition, but it is still small enough to discuss in ordinary language. The deeper change arrives when qubits are combined. Two qubits do not merely hold two separate uncertainties side by side. Under the right conditions, they can share one joint state that cannot be reduced to two individual stories. That is where the machine begins to leave the scale of a single delicate object and enter a wider space of relations. The qubit is the first departure. Many qubits are where the departure becomes a landscape. One qubit is strange, but it can still be held in thought. Two qubits begin to change the shape of the problem. Three make the change clearer. With each added qubit, the number of possible combined states doubles. The growth is not gentle. It does not move like stacking books on a table. It moves like a shoreline splitting into islands. Then coves, then smaller hidden inlets until the map no longer fits on the wall. This is where quantum computing stops feeling like a device made of parts and begins to feel like a controlled space of relations. A single classical bit has two possible settings. Two classical bits can form four possible arrangements, but at any instant they occupy only one of those arrangements. A register of classical bits is like a row of switches. Each switch has a definite position. A quantum register is not like that. Its qubits can hold a combined state in which many possible arrangements participate at once. The machine is not merely larger, it is using a different kind of size. The everyday comparison is a choir. One voice can sing one note, two voices can sing separate notes, but they can also form a harmony that belongs to neither voice alone. Add more voices and the important object becomes the pattern among them. A quantum register is not a pile of independent qubits. It can become a harmony of possibilities. The sound is not literal. The structure is. What matters is how the parts relate before the final measurement turns the pattern into a classical result. This corrects another false intuition. It is tempting to imagine that each qubit simply carries its own private mixture of 0 and 1. If that were all, the machine would not be nearly as powerful. The deeper resource appears when qubits are linked so that their joint state cannot be described by listing each qubit separately. The state belongs to the group, the visible parts are not enough. The relation is the object. This kind of linkage is called entanglement. Entanglement means that separate quantum systems share one state that cannot be fully reduced to its pieces. One sentence defines it. Two examples make it clearer. A pair of entangled particles can produce coordinated results even when measured far apart. A set of entangled qubits can store relationships that no ordinary collection of bits can copy efficiently. It matters because without entanglement, most quantum advantage disappears. Entanglement is not an added decoration. It is one of the load-bearing beams. As the number of qubits grows, the combined state becomes harder to represent with classical information. 10 qubits can involve a little more than 1,000 possible basis states. That is still easy to say. 50 qubits can already strain classical simulation. 100 qubits point toward a space so large that writing down every amplitude becomes unrealistic for any ordinary machine. The translation of scale is important. The chip may fit in a hand, but the full mathematical description can exceed what a warehouse of conventional memory could hold. The small object contains a vast description. That sentence sounds impossible only if size is judged by volume. In quantum mechanics, physical size and state space size are not the same thing. A few atoms can require an enormous description. A mod circuit can represent more structure than a classical computer can comfortably track. The fingertip-sized circuit is not large in space, it is large in possibility. That is the paradox. The machine is physically compact and mathematically immense. The visual anchor is a tiny silver landscape under glass with lines etched so finely they look calm and almost decorative. Nothing on its surface announces the scale it commands. No corridor opens, no engine turns, yet inside the controlled state of its qubits. A calculation moves through a space too broad for direct classical bookkeeping. It is like watching a still pond while the depth beneath it rearranges itself. The surface gives away very little. The mechanism also reveals a limit of observation. During the calculation, the full quantum state cannot be inspected directly. Measuring it would force a definite outcome and destroy the coherent pattern that makes the computation useful. The most important part of the process is therefore hidden not by secrecy, but by physics. To observe the entire state in the ordinary way would be to end the very state being observed. The instrument must work in the dark. This does not mean scientists are guessing blindly. They design circuits, predict statistical outcomes, run the machine many times, and compare the distribution of results with theory. A single readout gives only one classical outcome. Many readouts reveal the shape of the underlying process indirectly. The situation resembles learning the motion of wind by watching fields of grass bend over time. The wind itself is not held in the hand. Its pattern becomes known through repeated traces. The consequence is subtle and practical. A larger quantum computer is not automatically better. If the qubits cannot be controlled, linked and protected, the vast state space becomes useless noise. More qubits create more possible power, but also more ways for the system to fail. The beauty of the phenomenon does not remove its physical cost. Every additional qubit opens a larger space and adds another doorway for error. This is why scaling is so difficult. The machine must grow without becoming ordinary. It must add qubits without letting the surrounding world learn too much about them. It must create entanglement without creating uncontrolled disturbance. It must preserve an immense pattern long enough for a useful answer to form. At that distance from common experience, intuition has little to offer. Ordinary machines become more reliable by making their parts stable and readable. Quantum machines become useful by keeping some of their most important internal facts unreadable until the correct moment. That reversal is easy to state and hard to engineer. It is one reason the subject widens from computation into physics itself. The register of many qubits is a new kind of laboratory. It lets researchers prepare states that nature rarely presents in a clean form. It also asks whether the mathematical space used by quantum theory is merely a calculation tool or something more physically meaningful. If a small device can move through a state space no classical description can follow, then the word inside becomes less simple. The next layer turns that question into a reframe. The marvel is not that the chip contains many parts. The marvel is that its useful size may be hidden in the relations among possibilities, not in the visible machinery. The first reframe begins when speed stops being the center of the story. A quantum computer can be faster than a classical machine on certain tasks, but speed is only the surface symptom. The deeper change is not that the machine races through the same road more quickly. It may be using a road that classical computation cannot enter at all. This distinction matters because it changes the question from engineering to ontology. The task is no longer only to ask how fast the chip is. The harder question is what kind of physical space the chip is using while it calculates. A classical computer leaves a familiar trail. Electrical signals move through circuits. Memory cells change state. Logic gates transform definite inputs into definite outputs. Even when the process is complex, it can still be imagined as a long sequence of definite transitions. Slow the machine down enough and each step can be described in classical terms. The path may be complicated, but it is still a path. Quantum computation is not so generous. During the most important part of the calculation, the machine cannot be described as following one definite route through its possible states. It evolves as a whole pattern. The path is not hidden in the ordinary sense. It is not waiting in a drawer. There may be no single path to reveal. The everyday comparison is a footprint in fresh snow with no visible person nearby. The footprint is real. Its shape can be measured. It proves that something physical happened. But if the surrounding landscape contains no ordinary trail, the mind is forced to rethink what counts as a walker. A quantum computer leaves statistical footprints. It produces outcomes with patterns that match quantum theory. Yet the inner process does not resemble a classical journey from one definite state to the next. The result arrives. The route resists being pictured. This does not make the machine mystical. It makes it precise in an unfamiliar way. The equations tell engineers how to prepare the state, how to transform it, and how to extract useful results. The problem is not prediction. The problem is interpretation. The map works. The terrain remains contested. One interpretation says the quantum state represents something physically real. Another says it represents information available to an observer. Another says the apparent single outcome is only one branch among many. Each interpretation can guide the same successful calculation. Each gives a different answer to what exists while the chip is running. What seemed secondary now becomes central. Earlier, the qubit looked like the main novelty. Then the growth of many qubits seemed like the main novelty. But the deeper novelty is the status of the quantum state itself. Is it a real physical object, spread across a vast space of possibilities? Is it a compact expression of knowledge? Is it a book of probabilities waiting for interaction? Or is it a description of a branching reality where every outcome continues somewhere? The chip does not choose among these pictures. It simply works within the mathematics they all share. This is the uncomfortable success. It is useful to imagine a ship navigating by stars it cannot explain. The navigator reaches harbour night after night. The method is reliable. The predictions are exact enough to cross oceans. Yet the true nature of the stars remains under debate. Quantum engineers are in a similar position, though their stars are amplitudes phases and entangled states. The harbour is a measured result. The voyage is mathematically controlled. The meaning of the sea is still open. There is a concrete consequence. If the quantum state is physically real, then a quantum computer is manipulating an object far larger in description than its visible hardware suggests. If the quantum state is only information, then the world is telling us that information has a more basic role than ordinary matter seems to allow. If many worlds is correct, then the calculation may involve branches of reality that never meet again in ordinary experience. None of these options is mild. The simple machine forces serious choices. Human intuition reaches a limit here because it evolved around objects that persist occupy places and reveal themselves through contact. A stone can be photographed from many angles. A tree can be touched without destroying the question of where it stands. A quantum state cannot be exposed in this way. The complete state of many qubits cannot be copied and examined like a drawing. The act of trying to read it changes what can be known. The evidence must be collected through carefully repeated experiments, not through a single transparent view. What matters most cannot be watched directly. That is why benchmark results feel so strange. A machine runs a task designed to be difficult for classical simulation. It returns samples whose pattern can be tested. The more the pattern matches theory, the stronger the evidence that the quantum process was maintained. But the process itself does not become visible. The result is like hearing a complex chord from behind a closed door. The harmony proves the instruments are there. It does not let the eye see every string vibrate. The reframe also changes how earlier sections should be understood. The branching maze was not merely a metaphor for many possible answers. The qubit was not merely a better switch. The many-qubit register was not merely a larger memory. These were steps toward a stranger realization. Quantum computing works by preserving relations among possibilities that classical reality does not display openly. The power comes from an intermediate realm between preparation and measurement, where the rules are exact but the picture is not settled. It does not seem like much, but it changes everything. The visible chip is only the handle. The calculation is the hidden motion of a state that may not fit inside any ordinary image of space. A quiet processor in a cold chamber therefore becomes more than a device. It becomes a question made of metal microwave pulses and statistics. It asks whether physical reality is built from definite things, or from relations that become definite only under the right conditions. The next layer is why those relations are so hard to preserve. The machine can only use its strange working space while the surrounding world remains almost perfectly silent. The strange working space of a quantum computer does not vanish because it is imaginary. It vanishes because the surrounding world is too good at noticing it. A qubit can preserve a delicate relation between possibilities only, while that relation remains protected from uncontrolled interaction, heat vibration, stray radiation, imperfect materials. And nearby electronics all become potential witnesses. The danger is not that the qubit is physically weak. The danger is that its most useful information can leak away before the calculation finishes. That leakage has a name. It is called decoherence. Decoherence is the process by which a quantum system loses its ability to show interference because its state becomes entangled with the environment. A simple example helps. A dust grain floating in sunlight is struck by countless photons, and each scattered photon carries away information about where the grain is after enough scattering. The grain no longer behaves like a clean quantum object, it behaves classically. This matters because classical reality is not separate from quantum reality. It is what quantum reality often looks like after the environment has copied too much of it. The everyday comparison is a coffee cup on a table. It appears solid, definite, and comfortably ordinary. It has a position, it has a shape. It does not seem to hover among alternatives. But that stability is not a sign that quantum rules have stopped applying. It is the result of constant interaction. Air molecules strike the cup. Infrared radiation carries heat away. Light bounces from its surface into the room. Every contact spreads information about the cup into the environment. The cup becomes classical because the world keeps taking notes. This corrects a deep intuition. It seems that large objects are classical because largeness itself cancels quantum behavior. That is not quite right. The decisive part is not size alone. It is exposure. A large object has many ways to interact with its surroundings, so its quantum coherence disappears with extraordinary speed. A small object can also lose coherence quickly if it's exposed. A large engineered system can preserve coherence briefly if it is isolated with enough care. The boundary is not a wall, it is a process. What appears stable depends on leakage. The visual anchor is quiet and precise. Picture a warm object in a dark room surrounded by invisible messengers. Photons leave it in every direction. Molecules brush against it and depart. Tiny vibrations pass through the table beneath it. Each messenger carries a fragment of information. None has to carry the whole story. Together they make the object available to the world. That availability is what makes the object seem definite. The hidden cost of being real to many observers is the loss of fragile quantum possibility. A quantum computer must resist this natural process. It must keep its qubits from being recorded by the room, the wires, the support structure, and even the materials from which the chip is made. This is why the machine is cooled to temperatures near absolute zero. Cold reduces thermal motion. Shielding reduces unwanted radiation. Careful fabrication reduces microscopic defects. The goal is not comfort for the machine. The goal is silence. A qubit needs a darkness so complete that possibility can remain unreported. Yet the same machine must also be controlled. Microwave pulses must enter. Signals must be timed. Gates must be performed. Later measurements must be taken. The hidden dependency is now clear. Computation requires contact, but coherence requires isolation. Too much isolation leaves the machine unreachable. Too much contact turns it classical. The useful region lies between two failures. It is a narrow ledge. The chip balance is there. This is why decoherence changes the meaning of earlier success. The vast state space of many qubits is not automatically available. It must be kept coherent long enough for interference to matter. Without coherence, the many possibilities stop behaving as a coordinated pattern. They become noise. The machine may still produce bits but not useful quantum computation. The visible hardware remains. The quantum advantage disappears. Decoherence therefore explains why quantum behavior is not obvious in daily life. It is not absent. It is hidden by entanglement with the environment. The chair, the wall, the cup, and the air all have quantum descriptions in principle, but their relevant phase relationships are dispersed into so many environmental degrees of freedom that no ordinary observation can recover them. The information is not always destroyed in the simple sense. It becomes inaccessible. It is like a sentence torn into dust and scattered across a continent. The letters still exist somewhere. The message is gone for any practical purpose. This also exposes a limit of observation. The environment is not a passive background, it participates. It selects which features become stable enough to be seen by many observers. Position, shape, and certain energy states survive because they are copied repeatedly into the surroundings. More delicate relations fade from accessible experience. Human perception inherits the world that decoherence leaves behind. The classical world is the surviving public layer. The private quantum layer is mostly lost before it can be noticed. For a quantum computer, this is both obstacle and guide. Engineers study how errors appear, how quickly coherence decays, and which kinds of disturbances are most damaging. They design qubits with longer coherence times. They tune pulses so operations finish before the state degrades. They build codes that detect and correct certain errors without reading the forbidden information directly. The work is not simply to build colder machines. It is to manage what the environment is allowed to know. The consequence is real. A machine can have many qubits and still be useless if decoherence wins too quickly. Another machine with fewer qubits can be more meaningful if it preserves their relations longer. This is why raw qubit count is an incomplete measure. A quantum computer is not a warehouse where more boxes always mean more capacity. It is closer to a musical instrument whose value depends on how long its notes stay in tune. The note may be faint. The tuning is everything. There is a calm irony in this. The same process that makes the ordinary world reliable makes quantum computation difficult. Decoherence gives the cup its definite place, the table its stable surface, and the laboratory its shared reality. But it also tries to erase the very interference a quantum processor needs. The machine must carve out a temporary exception to the everyday world. It must preserve what daily experience continuously destroys. The next difficulty follows naturally. If decoherence cannot be eliminated completely, then the machine must learn to survive mistakes while still remaining quantum. That is where fragility becomes an engineering problem, and where error correction begins to change the future of the field. Error correction begins with an almost impossible demand. A quantum computer must discover that something has gone wrong without discovering the very information that makes the qubits useful. In an ordinary computer, this is straightforward. A bit should be 0, but it has become 1. The machine can inspect it, compare it, and repair it. Classical information tolerates being looked at. Quantum information does not. A careless inspection collapses the state and ends the computation. The repair must happen without opening the box too fully. That is the sharper vulnerability. The system is not only fragile because the outside world can disturb it, it is fragile because even protection can become a form of damage. The difficult thing is not noticing every detail. It is noticing only the right kind of detail. A doctor can measure a pulse without reading a thought. A quantum error correction system must do something similarly selective. It must identify whether a certain kind of error has occurred while leaving the encoded quantum state intact. This sounds like a contradiction. It is not. It is one of the most careful ideas in modern physics. The trick is to spread one fragile piece of quantum information across many physical qubits. The information no longer lives in one place. It lives in a pattern. A useful image is a message written into the arrangement of lanterns across a dark hillside. One lantern can flicker, another can dim, but the message is not stored in any single flame. It is stored in the relation among many flames, by checking limited features of the pattern. A watcher can learn where the disturbance happened without reading the message itself. Quantum error correction works in this spirit. It protects information by making it collective. The individual parts remain vulnerable. The pattern can survive. This introduces the distinction between physical qubits and logical qubits. A physical qubit is the actual piece of hardware, such as a superconducting circuit or trapped ion. A logical qubit is the protected quantum unit encoded across several physical qubits. The physical qubits are the fragile carriers. The logical qubit is the more stable pattern they form together. This matters because useful quantum computing depends on logical qubits, not merely on large numbers of physical ones. 1,000 delicate parts are not automatically a strong machine. Strength appears only when their errors can be organized and suppressed. Contrast is severe. Adding more physical qubits can make a system worse if each new qubit brings too much noise. More parts mean more places for trouble to enter. More wires, more controls, more microscopic defects. More opportunities for unwanted coupling. At first, scaling resembles adding more cracks to thin ice. It does not become safer simply by becoming larger. But below a certain error level, the logic reverses. More qubits can make the encoded state safer. Size becomes protection instead of danger. It does not seem like much, but it changes the future. This boundary is called the error threshold. The error threshold is the point below which error correction improves as more physical qubits are added. Imagine repeating a message across several careful scribes. If each scribe makes too many mistakes, adding scribes only creates confusion. If each scribe is reliable enough, comparison reveals the errors and the message becomes clearer. This matters because the threshold turns quantum computing from a fragile demonstration into a scalable technology. Above it, growth collapses. Below it, growth can help. The visual anchor is a fragile pattern preserved inside a storm. Wind moves through the structure. A few tiles shift, some signals arrive imperfectly. But guardians check the edges, not the secret center. They see the shape of the disturbance and correct it before the pattern loses itself. Nothing about this is effortless. The storm never stops. Error correction is continuous work. A quantum computer is not a machine that becomes perfect. It is a machine that keeps rescuing itself. Here, intuition reaches another limit. In ordinary life, redundancy means copying. A document is safe if many copies exist. A photograph can be stored on several drives. Quantum information cannot be copied in that simple way. The no-cloning principle forbids making an exact independent copy of an unknown quantum state. This rule prevents the obvious solution. The machine cannot protect a qubit by duplicating it like a file. It must protect the state indirectly through shared structure and carefully chosen measurements. The forbidden shortcut is what makes the engineering so subtle. The consequence is practical and enormous. A quantum processor with noisy qubits can show beautiful physics and still fail at long computations. Each operation may introduce a small error, over thousands or millions of operations. Small errors accumulate like dust on a lens. Eventually the answer blurs. Error correction is the method for wiping the lens while the image is still forming. Without it, quantum advantage remains limited to special demonstrations. With it, longer and more useful calculations become possible. The chip becomes less like a laboratory curiosity and more like a machine with a future. This is why recent progress in error correction carries more weight than a single speed record. A benchmark can show that a quantum system is difficult for a classical computer to imitate. Error correction shows whether the system can grow into something reliable. The first is a flare in the night. The second is a road. The road is still rough and it does not yet reach every promised destination. But its appearance changes the entire landscape. The earlier mystery now becomes more concrete. The question is no longer whether quantum states can exist. They can. The question is whether such states can be protected, manipulated, and scaled without losing their strange power. The answer is beginning to look cautiously positive. Not guaranteed, not complete, but no longer merely hoped for. The machine can make errors and still continue. That is a profound shift. It means fragility is not the end of quantum computing. Fragility becomes part of the design. The processor does not conquer noise by pretending it will vanish. It expects noise maps it and corrects it faster than it can spread. In that sense, a useful quantum computer is not a perfectly quiet object. It is an object that can remain coherent while surrounded by imperfect reality. The next layer follows from this threshold. Once errors can be reduced by adding the right kind of structure scale changes, meaning, again, more qubits are no longer only a threat under the right conditions. They become the path through the threat. The error threshold changes the emotional weight of the entire subject. Before it is crossed, adding qubits can feel like adding candles in a windy field. There is more light for a moment, but there are also more flames to lose. After the threshold is crossed, the same act begins to mean something different. More carefully arranged qubits can reduce error instead of multiplying it. The system does not become simple, it becomes survivable. That is the physical layer where consequence becomes measurable. The threshold is not a decorative milestone. It is a boundary between two futures. On one side, every larger machine becomes harder to trust. On the other side, larger machines can become more reliable when their parts are organized into the right protective pattern. This is the bridge that quantum computing has been trying to reach for decades. It does not promise instant usefulness. It promises a route. Without that route, the field remains a collection of brilliant demonstrations. With it, a practical machine begins to look like an engineering problem rather than a contradiction in nature. A bridge is the right image, but only if it is imagined carefully. Picture stones placed across a river in darkness. The first stones do not yet make a crossing. They only interrupt the current. Add them badly and the water becomes more chaotic. Add them in the correct pattern and a path appears. The river still moves, the stones still feel pressure. But a traveller can begin to cross. Quantum error correction works in a similar way. The noise remains. The world still touches the machine. The difference is that the structure now channels damage before it destroys the calculation. This is why a reduction in logical error is so important. A physical error is a mistake in one hardware qubit or one operation. A logical error is a failure of the protected encoded qubit itself. The distinction matters. A machine can tolerate many small physical disturbances if they do not combine into a logical failure. In ordinary terms, it is the difference between a cracked tile and a collapsed roof. The crack is serious. The collapse is decisive. Quantum engineering aims to keep cracks from becoming collapses. At first glance, the improvement may sound modest. A logical error rate drops by a factor of 2 when the code grows. That is not the kind of number that fills the imagination. But in scaling, repetition matters more than spectacle. A factor of 2 repeated across larger codes becomes a path toward extremely low error rates. The quiet improvement is the point. Useful quantum computing is not built from one miraculous leap. It is built from a trend that continues when the system grows. The trend is the evidence. The consequence reaches beyond the laboratory. If logical qubits become reliable enough, quantum machines can run long algorithms that are impossible today. They can simulate molecules with a directness classical machines cannot match. They can test materials whose behavior depends on tangled quantum interactions. They can explore certain mathematical problems where ordinary computation drowns in combinations. And yes, at sufficient scale, they threaten forms of encryption that protect much of modern digital life. The stake is not abstract. A better protected qubit eventually becomes a new industrial force. Still, this should not be exaggerated. Crossing a threshold is not the same as arriving at the final machine. A protected logical qubit may require many physical qubits. A useful processor may require many logical qubits. A powerful fault-tolerant machine may require vast systems of control, electronics, cooling, fabrication, calibration, and error management. The gap remains large, but the nature of the gap changes. It is less like asking whether flight is physically possible. It is more like asking how to build stronger wings, safer engines, and longer runways. The limit of intuition appears again. In ordinary engineering, scale often reveals weakness. A small bridge model survives. The full bridge must carry wind-weight corrosion. And time. Quantum engineering faces that same problem, but with an added reversal. The thing being protected is not a static structure. It is a state of possibility. It cannot be inspected too directly. It cannot be copied freely. It must be inferred through allowed measurements and preserved through patterns. The bridge is made of rules as much as material. The visual anchor is a cold processor with a hidden rhythm of checks running across it. Some checks ask whether neighboring qubits still agree in the right way. Others reveal where an error may have slipped in. The machine does not ask what the protected information is. It asks whether the protective fabric has torn. That difference is everything. A tailor can mend cloth without reading the letter wrapped inside it. Quantum error correction is that kind of repair. It protects the envelope without opening it. This physical layer also clarifies why measurement is not merely an ending. In a corrected quantum computer, measurement becomes part of the internal maintenance. Some qubits are measured repeatedly to detect errors, while the logical information remains hidden in the larger pattern. Measurement is no longer just the final act where a result appears. It becomes a controlled tool that can reveal damage without revealing the protected answer. The same force that can destroy a quantum state can also help preserve it if used with discipline. That is the paradox at the heart of the threshold. The machine survives by allowing carefully chosen contact with the world. Not all observation is fatal. Wrong observation is fatal. Correct observation becomes medicine. The surrounding environment measures randomly and damages the state. The engineered system measures selectively and repairs the state. The contrast is exact. Nature leaks information outward. The machine harvests only the information needed to stop the leak. From this layer, the earlier sections begin to settle into one shape. Qubits create possibility. Entanglement turns separate parts into a shared state. Decoherence threatens that state by spreading it into the environment. Error correction fights back by encoding the fragile information into a larger structure. The threshold proves that the fight can become favorable. What changes is not the strangeness of quantum mechanics. What changes is the degree to which that strangeness can be domesticated without being erased. The word domesticated should be handled gently. Quantum behavior is not made classical. It is made useful while remaining quantum. That is the achievement. A useful quantum computer will not be a machine that removes uncertainty from nature. It will be a machine that guides uncertainty through a sequence of controlled transformations until a reliable answer can be extracted. It does not escape fragility, it organizes fragility. The next scale moves beyond one chip and one laboratory. The same quantum rules that make error correction possible also imply connections that do not fit ordinary distance. To understand why the machine's internal relations are so powerful, the map has to widen toward entanglement itself. Entanglement widens the map because it refuses to treat separation as the deepest fact. Two particles can move far apart and still belong to one quantum state. Their measurable results can show correlations stronger than anything allowed by ordinary local hidden instructions. This does not let a message travel faster than light. It does not create a cosmic telephone, but it does weaken a familiar comfort. Distance is not always enough to make two systems fully independent. The space between them matters. It is not the whole story. The basic image is simple. Prepare two particles together, then send them in opposite directions. One travels toward a laboratory on one horizon. The other travels toward a laboratory on another horizon. Between them lies open space, perhaps a city, perhaps mountains, perhaps the curve of Earth itself. Classical intuition says that whatever each particle will do must either be fixed before the separation or caused by some signal later. Quantum experiments deny that simple choice. The results are coordinated in a way that no local pre-written script can explain. The term has already appeared, but now it needs weight. Entanglement is a shared quantum state that cannot be fully broken into separate descriptions of its parts. A pair of gloves in two boxes is not entanglement, because each glove already has its handedness before the boxes are opened. Entangled particles are different because the measured properties are not simply waiting as fixed labels. It matters because quantum computers use this shared structure to make many qubits function as one coordinated system. The everyday comparison is not two dancers watching each other across a room. That would still imply signals and reactions. A better image is one pattern printed across two distant sheets before either sheet can be understood alone. Looking at one sheet reveals something about the whole pattern, not because paper sends a message, but because the pattern was never truly divided into independent stories. This is hard to picture. The difficulty is honest. Entanglement is not built for human imagination. Experiments have tested this difficulty with increasing care. Pairs of particles are measured in ways chosen after the particles are far apart. If the world were governed by local hidden values, the correlations should obey certain limits. They do not. The measured outcomes violate those limits. Again and again, with photons, atoms, ions, and solid-state systems, the same result appears. The visible distance grows. The quantum relation survives. That result does not mean anything can influence anything else in a reckless way. Physics remains disciplined. No usable signal crosses space faster than light. No observer can control the distant outcome to send a sentence. The correlations become clear only when the records from both sides are later compared through ordinary communication. The consequence is subtler than science fiction and more serious. Nature permits non-classical connection without permitting faster-than-light messaging. The rule is stranger than a simple violation. This is where intuition reaches another limit. Everyday reasoning treats objects as carriers of their own private properties. A stone has its weight whether it is weighed or not. A compass needle points in a direction even when no one is watching. Entangled systems do not fit that picture. The property revealed at one side is tied to the measurement context and to the shared state. The relation is more basic than the separate inventory. The parts do not fully own their facts. The visual anchor is two faint lights at opposite edges of a dark plane. Each light flashes when measured. No beam passes between them, no visible cord connects them. Yet after the records are placed side by side, a hidden order appears with a precision that chance cannot explain. The order does not live in the empty space between the lights. It lives in the quantum state that described them before the flashes were recorded. Quantum computers bring this cosmic lesson down into hardware. Inside a processor, qubits must become entangled in carefully arranged patterns. A calculation is not merely a set of independent qubits changing at once. It is a fabric of shared states. Some operations create entanglement, others rotate phases, others guide interference. The final result depends on how the whole fabric evolves. Remove entanglement, and the fabric becomes a loose pile of threads. The quantum advantage largely fades. The scale shift is important. Entanglement can be tested across long distances, but it can also be engineered across microscopic circuits. The same principle links laboratory demonstrations with computation. On one side, particles separated by great distances challenge local realism. On the other, neighbouring qubits inside a cold chip create useful non-classical structure. The scale changes from horizons to micrometers. The rule remains recognisable. Separate pieces can belong to one state, This also shows why quantum networks matter. If entanglement can be distributed between distant devices, then quantum computers may eventually connect in ways that ordinary machines cannot imitate exactly. Secure communication, distributed sensing, and linked quantum processors all rely on preserving entanglement beyond one chip. The dream is not just a faster isolated machine. It is a wider quantum infrastructure where shared states become a resource. That future is difficult because the environment keeps trying to record and destroy the delicate relation. Entanglement is powerful but not invincible. Fibers lose photons, detectors miss events, materials introduce noise. The same decoherence that threatens a chip threatens long-distance quantum links. The beauty of the relation does not remove the cost of maintaining it. Every kilometer, every connector, and every interface becomes a place where the shared state can fade. A meaningful consequence follows. The universe appears local in daily life because decoherence and limited observation hide these relations from view. Tables, buildings, and planets do not show obvious entanglement across their large parts in a way that can be used casually. Their quantum relations are dispersed into the environment too quickly. The classical world is the quiet mask left behind. Beneath it, the rules still allow connections that do not fit the old picture of separated objects. Entanglement therefore enlarges the central question. The quantum computer is not only using superposition inside individual qubits, it is using relations that challenge the ordinary meaning of separateness. Its power is not stored in parts alone, but in the way parts become one state. From here, the next reframe becomes unavoidable. If separate things do not always have independent facts, then measurement itself cannot be treated as a passive act. The question asked of a quantum system helps decide what kind of answer can become real. Measurement sounds like the simplest part of physics. A system has a property, an instrument checks it. The answer appears. That picture works well enough for falling stones, warm cups, and planets moving through the dark. It fails us at the quantum level. A measurement is not merely a window opened onto a pre-written fact. In many cases, it is part of the event that allows a particular fact to become definite. The question does not only reveal the answer, it helps define what kind of answer can exist. This is the second major reframe. Earlier, the quantum state seemed like the strange part, and measurement seemed like the ordinary ending. But the ending is not ordinary. The final contact with the world is one of the deepest puzzles in the theory. Before measurement. A qubit evolves according to smooth mathematical rules. After measurement, one definite outcome is recorded. The transition between those two descriptions is practical, reliable, and unresolved. It is the place where possibility becomes record. A useful everyday comparison is a dark room with several doors. Behind each door is not simply the same object waiting to be viewed from another angle. Opening one door changes which arrangement becomes available. The room does not offer every answer at once in a classical inventory. The door chosen is part of the result. Quantum measurements behave in a related way. Different experimental questions do not merely uncover different hidden labels. They can define different contexts in which outcomes become meaningful. The technical word is contextuality. Contextuality means that a quantum result can depend on the whole measurement arrangement, not only on the property being asked about. A violin string gives different tones depending on where it is touched, how it is bowed, and what resonances surround it. The note is not stored as a single isolated fact before the performance. This matters because quantum systems cannot always be assigned a complete set of pre-existing values that all possible measurements would simply reveal. The consequence is profound. A particle does not always carry a full private list of answers. It may carry a state from which answers emerge when a particular kind of question is imposed. That sounds like a weakness in knowledge, but it is not. Experiments rule out the simpler idea that all the answers were merely hidden. The world is not withholding a classical ledger from view in some cases. There is no ledger of that kind to find. This changes the role of the observer, though not in a mystical sense. Consciousness does not need to be invoked for ordinary quantum measurement. A detector, a molecule, a photon field, or a measuring device can all create the relevant interaction. The important point is physical coupling. The quantum system becomes linked with something that can carry a stable record. Once that record spreads into the environment, the result becomes part of the classical world. A mark appears, a counter clicks, a bit is stored, the event enters shared reality. It is worth pausing over the contrast. Before measurement, the system can preserve alternatives that interfere. After measurement, one outcome stands in the record and the interference between alternatives is no longer available in the same way. The delicate structure has been converted into a public fact. This is useful and costly at once, or without measurement there is no answer. With measurement too early, there is no quantum computation. The door must open, but only at the right time. A quantum computer is therefore built around disciplined postponement. It prepares qubits, it entangles them, it rotates their phases, it allows amplitudes to reinforce or cancel during this period. The machine must prevent premature records from forming in the environment. Only after the calculation has shaped the probability landscape does it read the qubits. The measured bit string is not the whole quantum process. It is the fossil left by that process. The life of the calculation has already passed into one trace. The visual anchor is the camera with a shutter that cannot be opened early. If it opens too soon, the faint image is ruined. If it never opens, nothing is captured. The art lies in letting the exposure develop in darkness, then making a single record at the correct moment. Quantum measurement works with a similar discipline. It turns hidden structure into visible data, but the act of visibility changes what remains. Human intuition reaches its limit because ordinary perception hides this cost. Looking at a mountain does not noticeably reduce the mountain's ability to be a mountain. Reading a sign does not collapse a landscape of alternatives, but quantum states are small enough, isolated enough and coherent enough that interaction changes their future possibilities. Observation is no longer a passive gaze. It is an event in the same fabric as the system being observed. This is why delayed choice experiments feel so unsettling. They show that the way a quantum event is finally measured can determine whether its earlier behavior is best described as wave-like or particle-like. This should not be turned into cheap time travel. No usable message is sent into the past. Yet the experiments still weaken the classical idea of a single, fully determined microscopic history. The past of a quantum system is not always a trail of definite footsteps. Sometimes it is a pattern completed only by the whole experimental arrangement. The consequence for reality is quiet but severe. Facts at the quantum level are not always like stones lying in a field. Some are more like notes that exist only within a completed piece of music. Remove the context and the note no longer has the same meaning. Change the measurement and a different structure becomes relevant. This does not make reality subjective in a casual sense. It makes reality relational in a precise physical sense. The answer belongs to the interaction. In the quantum computer, this reframe becomes engineering. A measurement at the wrong moment ruins the calculation. A measurement designed for error correction can help preserve it. A final measurement extracts the result. The same general act can destroy, protect or reveal depending on how it is arranged. That is why the machine feels like a study in controlled contact. It must decide when the world is allowed to know. The central paradox now has another side. Quantum computation depends on states that are not yet classical facts, but its usefulness depends on turning them into classical facts at the end. The machine lives between silence and record. It is powerful because it delays certainty, and useful because it finally produces certainty. The next layer gathers the pieces together. Superposition, entanglement, decoherence, correction and measurement are not separate curiosities. They are parts of one larger story about information and what survives long enough to be called real. The pieces now begin to fit together, but not as a simple chain. Superposition is not one topic entanglement, another decoherence, a third and measurement, a final switch. They are different faces of one larger process. A quantum computer works by preparing information in a form that is not yet classical, linking parts of that information into shared states, protecting those states from the environment, correcting the damage that still occurs, and finally allowing a record to form. The whole story is about what can be preserved. It is also about what must be lost. Information is the thread that runs through every layer. In ordinary speech, information sounds abstract, like words on a page or numbers in a file. In physics, it becomes more concrete. Information is the pattern that distinguishes one possible state from another. A hot object, a spinning particle, a molecule, and a computer memory all carry information because they could have been arranged differently. This matters because quantum machines suggest that information is not merely something matter stores. It may be part of how matter behaves. A classical object seems to have properties first and information second. A stone has a position, and that position can be written down. A quantum system reverses the emphasis. The state is a structure of possible information, and definite properties emerge when the right interactions create stable records. The stone-like picture is not wrong at human scale. It is incomplete. It is the public face of a deeper accounting. The object appears solid because enough information about it has become stable and redundant. A useful image is a loom working in darkness. Some threads become tight and visible as cloth. Others remain loose, hidden, and unable to carry a shared pattern. Decoherence pulls certain threads into the environment, measurement knots some of them into records. Error correction keeps selected threads from being stolen too early. Entanglement ties distant threads into one design. The fabric that finally appears as classical reality is not the whole loom. It is the part that survives exposure. This changes the meaning of stability. A table seems stable because it endures when viewed from many angles. Several observers can enter the room, see the same table and agree on its location. That agreement feels basic, but at a deeper level, agreement may be the outcome of information copied many times into the environment. Light bouncing from the table carries position and shape to many eyes and cameras. Air, heat, and surrounding objects also receive traces. The table becomes objective because its accessible features are widely recorded. The visible part is not the decisive part. The decisive part is the copying. This is where earlier scales interact. Superposition is the preservation of alternatives that can still interfere. Entanglement is the sharing of a state across parts. Decoherence is the uncontrolled spread of information into the environment. Measurement is the formation of a stable record. Error. Correction is the engineered refusal to let the wrong information escape. These are not isolated marvels. They are movements of information between hidden coherence and public fact. The consequence is that a quantum computer is best understood not as a faster calculator, but as a machine that controls the boundary between private and public information. During computation, the relevant information must remain private to the quantum state. It cannot be fully copied into the environment. It cannot be read as a classical list at the end. A small part of it must become public as an answer. The machine's art lies in deciding what remains hidden, what is corrected, and what is finally allowed to appear. Human intuition reaches a limit here because it treats reality as already public. The world seems to arrive fully formed. Objects appear to possess their features whether or not anything records them. This assumption works so well in daily life that it feels impossible to question. But quantum mechanics shows that public facts may be a special outcome, not the starting point. The shared world is what remains after the deeper state has interacted, leaked, and stabilized in certain ways. The physical image is a shoreline after the tide has withdrawn. The wet sand shows clear marks. Shells, stones, and ridges are visible. It is tempting to think the shore was always exactly this pattern, but the water shaped it, erased parts of it, and left other parts behind. The classical world is like that exposed shore. It is real, but it is not the full motion that produced it. The quantum process is the tide that cannot be frozen without changing the scene. This view does not dissolve matter into fantasy. Matter is still real. Energy is still real. Detectors still click. Chips still warm and the planets still move under gravity. The point is more careful. The familiar categories may not be the most fundamental ones. Matter and energy may be stable patterns in a deeper quantum informational structure. The things seen every day are not illusions. They are emergent. They are reliable because the underlying processes make them reliable. What appears solid may be a successful pattern of persistence. Quantum computers sharpen this idea because they create small islands where different rules remain exposed. Inside the protected processor, information is not yet forced into the public classical layer. Relations among possibilities still matter. Interference still shapes outcomes. Entanglement still binds parts into one state. The machine holds back the tide for a moment, not forever. Then it releases a result. This is why the laboratory device becomes a model of the larger transition from quantum to classical. One meaningful consequence is practical. If engineers learn to control this boundary more skillfully, they may simulate molecules, materials, and physical systems that classical machines struggle to represent. Chemistry itself is quantum information arranged into steel forms. A drug molecule folds bonds and reacts according to interactions that are difficult to approximate fully. A quantum computer does not merely calculate those interactions from outside, it can mirror their structure more naturally. The tool resembles the problem. Another consequence is conceptual. If information is the connecting thread, then questions about quantum mechanics. Black holes, computation, and space-time begin to touch. A black hole appears to hide information. A quantum computer protects information. Decoherence spreads information. Measurement records information. These are different arenas, but the same word keeps returning with physical force. The repetition is not poetic, it is a clue. The map is becoming more coherent. Yet a limit remains. The machine's operations can be predicted, tested, and improved. But the deeper interpretation of the quantum state still cannot be chosen by the current evidence alone. Several maps still fit the same coastline. The next section moves into that observational limit, where uncertainty is not a weakness of the science but one of its most precise features. The deepest limit in this story is not a lack of data. It is more delicate than that. Quantum mechanics has been tested with extraordinary precision and its predictions keep surviving. Experiments agree with the equations, devices built from the equations work, yet the same successful mathematics can be placed inside different pictures of what reality is doing. The measured shore is clear, the ocean beneath it has more than one possible map. That is why interpretation remains hard. A theory can be excellent at predicting outcomes while still leaving the meaning of its internal objects unsettled. The quantum state is the central example. It allows scientists to calculate probabilities with astonishing accuracy. It tells engineers how to design gates, pulses, and error correction codes. But what is the quantum state itself? A physical wave spread through a vast abstract space. A book of knowledge held by an observer, branching structure where all outcomes continue, a tool for predicting future experience. The answer is not directly visible in the result of one experiment. At first glance, this seems like a weakness. A mature science should say what its objects are, but quantum theory is not vague in the places where it makes contact with measurement. It is almost brutally precise. Prepare this state, perform this operation, measure in this way. The probabilities follow. The uncertainty enters when asking what happens between preparation and measurement in a picture that can be carried by human intuition. The equations do not fail there. The imagination does. The visual anchor is a table covered with several transparent maps. Each map outlines the same coastline, the same bays, the same headlands, and the same harbour. One map marks ancient currents, another marks depth, another marks shipping lanes. From above, all seem to match the shore, but they tell different stories about what matters. In quantum mechanics, rival interpretations can match the experimental coastline while disagreeing about the underlying sea. Many Worlds offers one map. It says the wave function never collapses. All possible outcomes continue in separate branches and each observer experiences one branch from the inside. The advantage is that the mathematical evolution remains smooth and universal. The cost is enormous. Reality becomes vastly larger than the experienced world. Every quantum event opens a branching structure too broad to picture. The price of simplicity in the equations is multiplicity in existence. Collapse theories offer another map. They say the wave function really does collapse, not merely as an update of knowledge, but as a physical process. This gives measurement a definite mechanism. It also changes the usual equation slightly. That is important because such changes can in principle be tested. The stake is clear. If collapse happens physically, extremely delicate experiments may one day reveal where standard quantum mechanics breaks. So far, no confirmed break has appeared. Pilot wave theory offers a different route. It gives particles definite positions guided by a wave that evolves according to quantum rules. This restores a kind of underlying definiteness, but only by accepting a guiding structure that is deeply non-local. The particle has a path. The wave that guides it is not limited in the classical way. The comfort of definite position is purchased by surrendering the comfort of ordinary locality. There is no free return to the old world. Other interpretations treat the quantum state more as information than as a physical object. In these views, the wave function may describe expectations knowledge, or relations rather than a material wave. This can make the measurement problem feel less like a physical collapse and more like an update in what an agent can say, but the cost appears elsewhere. If the quantum state is information, whose information is it, and why does the world enforce such precise statistical rules? The answer must still carry the weight of experiment. This is the limit of direct observation. No one can place an interpretation under a microscope and see a label on it. Experiments reveal outcomes, correlations, interference errors, and successful predictions. They do not automatically reveal which philosophical image is correct. A detector does not click differently because a physicist prefers many worlds over collapse, or relational quantum mechanics over pilot waves. The click belongs to the shared formalism. The interpretation lives one layer deeper. This does not mean all interpretations are equal in every way. Some are mathematically cleaner. Some are easier to connect with relativity. Some make possible new experimental tests. Some require additional assumptions. Some are more economical in one sense and more extravagant in another. The debate is not empty. It is disciplined by consistency, simplicity, compatibility, and possible future evidence. But current quantum computers do not settle it. They sharpen it. A working quantum computer demonstrates that the formalism can be scaled into a controlled machine. It does not tell by itself. Which metaphysical picture must be chosen? This is an important restraint. A powerful chip does not prove that many universes exist. It does not prove that reality is only information. It does not prove that measurement creates the world in a casual human-centered sense. What it proves is more modest and more durable. Quantum rules can be engineered into a device whose behavior exceeds classical simulation for certain tasks. That fact is already enough to unsettle the classical picture. The extra interpretation must be handled with care. It is not only distance, it is access. Some parts of reality are not hidden because they are far away. They are hidden because the act that would reveal them changes the conditions under which they exist. The full quantum state cannot be copied for inspection. Many incompatible measurements cannot all be performed on the same individual system. The observer must choose a question and the choice limits the answers available. Knowledge is gained through carefully designed losses. The physical image is a dark observatory pointed not at stars but at a sealed quantum process. Each exposure reveals one pattern of light on a plate. No single exposure shows the whole sky. I'll repeat the process many times, changing the setup with care, and a statistical sky emerges. It is real. It is testable. Yet it remains different from standing outside the universe and looking at the complete state at once. There is no such external balcony available. The consequence for science is surprisingly calm. Uncertainty becomes structured. The unknown is not a fog where anything can be imagined. It has edges. The equations constrain it. Experiments narrow it. Technology probes it. Interpretations compete within it. The mystery is not generic. It is exact enough to build machines around, but not yet settled enough to become a single picture. That is a rare and fertile condition. It means future progress can come from two directions. Better experiments may reveal tiny deviations that favor one view. Larger quantum computers may simulate regimes where hidden assumptions become testable. New theory may reorganize the existing maps into a broader one that makes the old alternatives look partial. Any of these outcomes would change the meaning of the chip without changing the fact that it already works. The limit of knowledge is therefore not an ending. It's part of the instrument's significance. Quantum computers sit exactly at the boundary between what can be operationally mastered and what cannot yet be conceptually settled. They turn uncertainty into something active. The next section reorders the whole map around that fact. The machine is no longer only a product of quantum theory. It becomes a probe aimed back at the theory itself. The mature form of the paradox is now visible. A quantum computer is built from a theory whose predictions are trusted more deeply than almost anything in physics, yet the meaning of that theory remains unsettled. The machine is not waiting for philosophers to finish arguing. It runs, it samples, it corrects errors, it produces results. At the same time, every successful operation strengthens the very framework whose interpretation is still open. The tool depends on the mystery, and the mystery is tested by the tool. This is the cleanest reversal in the map. At the beginning, the processor seemed like an object to be explained. Now it begins to look like a system that explains the limits of explanation. It's not merely a faster machine sitting inside a laboratory. It is a controlled region where nature is prevented from becoming ordinary too quickly. Inside that region, possibilities can interfere. Relations can matter. More than parts and information can remain unavailable to the outside world until the final moment. The chip is a small manufactured exception to everyday reality. A helpful image is a lantern lowered into deep water. The lantern does not drain the sea. It does not reveal every current. But it makes a cone of motion visible where darkness usually hides everything. A quantum processor does something similar. It does not reveal the full ontology of quantum mechanics. It creates a controlled volume where quantum rules can be shaped, stressed, and measured with unusual clarity. The light is narrow. The depth is real. This reorders the earlier pieces. Superposition is not simply a strange property of tiny things. It is a way for a system to preserve more than one possible contribution before a record forms. Entanglement is not merely an exotic link between particles. It is the refusal of the world to be fully described as independent pieces. Decoherence is not just noise. It is the natural spread of information that makes the classical world appear. Measurement is not a passive glance. It is the creation of a stable public trace. Error. Correction is not a patch added to imperfect hardware. It is a method for keeping the quantum layer from dissolving too soon. The subject has transformed from an object into a system. What appeared at first as a chip is really a meeting point. Hardware, information, thermodynamics, measurement, and interpretation all converge there. A pulse sent into this processor is not only an electrical event, it is a command issued at the boundary between hidden quantum structure and public classical outcome. The readout is not only a number, It is the final trace of a process that could not be watched directly while it mattered most. The visible answer is the last page, not the whole book. This creates a precise contrast. Classical machines are understood by breaking them into parts and following the motion of signals. Quantum machines are understood by controlling the relations that cannot be reduced to parts alone. A classical failure often means a broken component, a bad wire, or a wrong instruction. A quantum failure may mean that the environment has learned too much too soon. The decisive event may be invisible. A photon scattered, a defect shifted, a phase drifted. The calculation lost coherence before it could finish speaking. The limit of intuition is therefore not just smallness, it is wholeness. Human thought is comfortable with objects that can be separated, named, and inspected. Quantum computation reveals systems where separation can destroy the thing being studied. The state is not a collection of little facts placed in little boxes, it is a structured whole. Touch the wrong part in the wrong way, and the whole reorganizes into a poorer, more classical form. This is why the machine must be treated less like a clock and more like a temporary weather system of possibility. The consequence is intellectually satisfying because it clarifies why no single metaphor has been enough. A qubit is not a coin, entanglement is not a hidden wire, measurement is not ordinary looking, decoherence is not simple forgetting, error correction is not simple copying. Each metaphor works for a few steps and then fails. The failures are useful, they reveal where the old concepts end. Science advances here not by finding one perfect image, but by learning exactly which images must be left behind. At larger scale, this changes how the universe itself is imagined. If matter behaves as stable information under constant environmental recording, then the classical world is not the foundation, it is the durable layer. If entanglement organizes what cannot be separated, then space may not be the deepest form of relation. If measurement creates public facts from private quantum structure, then reality is not a staged edge filled only with finished objects. It is a process that produces finished objects under specific conditions. The calm shock is that this process can be engineered. A quantum computer is not an escape from the universe. It is the universe arranged into an unusual posture. Metals, fields, cold timing, and mathematics are aligned so that the underlying rules remain visible for a short time. The machine does not violate the classical world, it delays the classical world. That delay is where the computation happens. That delay is the resource. It is also what makes the device a probe. By asking how long coherence can survive, how errors spread, how entanglement scales, and how logical qubits improve, researchers are not only improving technology, they are testing how far quantum mechanics can be pushed before some hidden limit appears. So far, no such limit has been found, the theory keeps holding. The machines keep improving, though the silence of failure is becoming meaningful. This does not mean the final interpretation has arrived. It means the mature paradox is stable enough to state plainly. The most accurate theory of microscopic reality can now be manufactured into working devices. While its deepest picture remains unresolved, that is not a weakness to be hidden. It is the shape of the frontier. The instrument is already useful and still philosophical. The calculation is practical and still metaphysical. From here, the descent toward closure can begin. The question is no longer whether the strange rules are real enough to matter. They are. The remaining task is to understand what their controlled use may change, and what kind of stillness remains when the machinery stops. The calm descent begins by separating promise from noise. Quantum computers will not make every machine obsolete. They will not turn all problems into easy problems. They will not replace ordinary computers for most daily tasks. Their importance is more specific and therefore more serious. They are suited to problems where nature itself is quantum, where classical bookkeeping expands too quickly, and where hidden structure can be shaped through interference, entanglement, and correction. The future is not magic, it is specialization with unusual depth. The first likely transformation lies in simulation. Chemistry is not classical at its foundation. Bonds, orbitals, reaction pathways, and material properties all depend on quantum behavior. Classical computers approximate these systems with remarkable skill, but the cost grows quickly as the systems become more complex. A quantum computer can, in principle, represent parts of that behavior more naturally. The tool resembles the object being studied. That resemblance may become one of the most important scientific instruments of the century. A concrete image helps. Imagine a laboratory bench with a molecule that cannot yet be built, a battery material that has never been tested, and a catalyst that might lower the cost of clean fuel. Today, each candidate must pass through layers of approximation, screening, synthesis, and experiment. A mature quantum computer would not remove the laboratory. It would change what reaches the laboratory. Fewer blind guesses, more precise candidates, a shorter path from possibility to testable matter. The consequence is practical, but it remains connected to the deeper theme. The same quantum rules that make a processor difficult to interpret may help design medicines, materials, and chemical processes. The strangeness does not stay in philosophy. It enters manufacturing, energy, medicine, and measurement. A state that once seemed too delicate to preserve may guide the design of objects that are solid, useful, and shared. The hidden layer becomes a tool for changing the visible layer. Encryption is another consequence, though it should be stated without alarm. Large fault-tolerant quantum computers could threaten widely used public key cryptography. This is not because they are generally omnipotent, but because certain quantum algorithms fit certain mathematical locks unusually well. The danger is specific. Systems based on factoring and related problems must be replaced by methods believed to resist quantum attack. That transition is already underway. The real tension is timing. If secure infrastructure changes before powerful quantum machines arrive, the risk can be reduced. If the machines arrive before the transition is complete, stored and intercepted data may become vulnerable. The difficult thing is not recognizing the threat. It is updating a global digital system slowly enough to be safe and quickly enough to matter. This is a very human consequence of a very non-classical technology. A cold chip in a shielded chamber can eventually affect bank records, medical archives, government systems, and private communication. The scale translation is almost strange in itself. A fragile qubit protected from a single stray disturbance may one day force changes across the internet. The workshop is quiet, the reach is planetary. There is also the future of measurement. Quantum systems can be used as sensors because they are sensitive to small changes in fields, forces, and time. The same fragility that makes them hard to protect can make them exquisitely responsive. A small disturbance that would ruin a calculation can become a signal in a sensor, gravity, magnetism. Acceleration and timekeeping may all be measured with greater precision through quantum devices. Here again, the weakness becomes a resource when it is controlled. What breaks one machine can empower another. The visual anchor is a quiet workshop at night. On one table, a design for a new molecule waits beside a screen of calculated energy levels. On another, a sensor listens for a field too faint for older instruments. In the corner, a cryptographic standard is being rewritten before a threat fully arrives. None of this looks cosmic at first glance, yet each task is connected to the same deep rule. Information, when arranged quantum mechanically, can reveal and reshape parts of reality that classical tools struggle to reach. The limit of intuition in this final approach is the temptation to demand either total revolution or total disappointment. New technologies are often described as if they must change everything immediately or mean very little. Quantum computing does not fit that rhythm. Its progress is uneven, demanding, and highly constrained. A useful machine may transform narrow fields before it touches ordinary life directly. The early effects may appear in chemistry databases, secure communication standards, and specialized simulations long before they appear as familiar household devices. Quiet change is still change. This restraint also protects the wonder from exaggeration. The most profound fact is not that quantum computers will do every imagined thing. They will not. The profound fact is that some useful tasks seem to become possible only by preserving behavior that daily reality normally hides. A future drug battery or sensor may owe its existence to controlled superposition and entanglement. The ordinary object will carry an invisible ancestry. It will be classical in other hand, but quantum in its design history. The broader scientific consequence is equally measured. Larger quantum computers may help test models of materials fields, and perhaps in aspects of fundamental physics that classical machines cannot handle well. They may not deliver a final theory of reality. They may not choose one interpretation of quantum mechanics, but they can make the space of possible answers narrower, sharper, and more testable. They can turn some questions that were once purely theoretical into questions with numerical structure and experimental direction. That is how mature science often advances, not by one thunderclap, but by better constraints. What has been resolved by this point is the reality of the strangeness. Superposition is not a metaphor. Entanglement is not a poetic link. Decoherence is not merely inconvenience. Measurement is not passive bookkeeping. Error correction is not simple redundancy. Each is a working part of a growing technology. The world has not become less strange. It has become more articulate. The strange features now have circuits, thresholds, diagrams, and failure modes. They can be calibrated. They can be improved. They can be used. The major tensions can therefore soften without disappearing. The chip is fragile, but fragility can be organized. Measurement is dangerous, but it can be timed and shaped. Noise is unavoidable, but it can be corrected below a threshold. Interpretation is unsettled, but prediction is powerful. The machine does not solve every philosophical question. It shows that unanswered questions can coexist with practical mastery. That coexistence is one of the clearest lessons of the field. The full shape is almost visible now. A quantum computer is not simply a fast device, not simply a proof of one grand worldview, and not simply an engineering challenge. It is a meeting place between useful control and unfinished understanding. The final step is to return to the cold processor, where the story began with less surprise and more clarity. The cold processor rests again in darkness. The calculation has ended. The pulses have stopped. Somewhere in the surrounding electronics, a final record has been written as ordinary bits. The machine that depended on uncertainty has returned a definite answer. This is the quiet shape of the whole story. A quantum computer does not remove mystery from the world. It gives mystery a disciplined form, cold enough, shielded enough, and precise enough to become useful. At the beginning, the central question seemed almost impossible to hold. What is a quantum computer actually touching when it works? The answer is clearer now, though not complete. It is touching the part of nature where possibilities can still interfere before becoming records. It is touching relations that cannot be reduced to separate pieces. It is touching information before that information has fully entered the public classical world. That does not prove one final picture of reality. It proves that the classical picture is not enough. The strongest lesson is not that the universe is one specific thing, such as a multiverse, a hologram, or a computation. Those ideas remain candidates, maps, and arguments. The stronger lesson is that nature permits working machines whose power depends on features that ordinary intuition cannot supply. Superposition matters, entanglement matters, decoherence matters, measurement matters, error correction matters. These are not ornaments around the science. They are the machinery of the science itself. A small visual image can hold the final contrast. On the laboratory floor stands a tall refrigerated tower, polished, layered, and still. Inside it, a chip sits near absolute cold, while the warm world continues outside with footsteps, voices, dust, and light. The visible room belongs to classical experience. The protected interior briefly preserves another kind of order. Then the answer comes out and joins the room. Possibility becomes record. The private state becomes public fact. This is not a failure of the quantum world. It is the way the quantum world becomes usable. Human intuition softens at this point. It no longer has to pretend that a particle is a tiny marble, or that measurement is only looking, or that distance always defines independence, or that the past of a microscopic system must resemble a trail of footprints. Those images were useful within their limits. They carried thought for a while, then they broke. Their breaking is not a defeat. It is how understanding moves beyond the scale where it was born. The meaningful consequence is not only technological. Yes, quantum computers may help design better materials, simulate chemistry, improve sensors, and force new security standards. Those matters are real. Yet the deeper consequence is that a working device has made old philosophical questions physically active. The machine does not merely invite wonder, it demands calibration, testing, cooling, shielding, timing, and proof. The mystery has entered the workshop. That gives it weight. The final map is calmer than the first impression. There is no need for loud claims. A quantum computer does not need to be described as supernatural, impossible, or beyond science. It is deeply within science. That is exactly why it matters. It follows equations that have survived every serious test. It fails in measurable ways. It improves through engineering. It produces data. Its strangeness is not outside the rules. Its strangeness is the rule. The limit of knowledge remains, but it is now precise. Current experiments do not select one final interpretation of quantum mechanics. They do not say once and for all whether all branches exist, whether the wave function is physical, whether collapse is real, or whether information is the deepest layer. They do show that any future answer must preserve the working facts. It must account for interference, entanglement, decoherence, measurement, and scalable correction. The unknown is no longer empty space, it is a shaped opening. It has boundaries made by experiment. This is why the processor can be understood as both a tool and a question. As a tool, it performs specific tasks by using quantum structure. As a question, it asks what kind of world allows such tasks to be performed at all. The same chip that may help calculate molecules also presses on the meaning of physical reality. That dual role is not a contradiction. It is the central beauty of the subject. Use and understanding advance together, but not always at the same pace. There is a final correction to make. The world revealed by quantum computing is not less real because it is less intuitive. It is not softer, weaker, or more imaginary. It is, if anything, more demanding. It requires more careful language, more careful measurement, and more careful humility. Classical reality remains real. The cup, the table, the night sky, and the body at rest all belong to the shared world. But they are not the full depth of it. They are the stable surface of a deeper process. The surface is dependable. The depth is still being explored. The central question returns with a gentler answer. What is doing the work inside the quantum computer? The most honest answer is that quantum reality itself is doing the work under conditions rare enough to be engineered and fragile enough to be lost. It is not ordinary parallel searching. It is not classical hidden machinery. It is controlled evolution of a state that holds possibilities, relations, and phases until measurement extracts a trace. The trace is small. The process behind it is not. The cold chip does not explain everything. It does not need to. It has already changed the question from whether quantum strangeness is real to how far that strangeness can be organized, protected, and understood. The machine waits in sequence after its calculation, and the silence feels different now. It is not empty. It contains the knowledge that beneath the familiar world, reality has rules more subtle than sight, more delicate than touch, and more exact than intuition. The work continues elsewhere in laboratories, equations, and future machines. For now, the process arrests, the answer is written, and the night can settle around the thought that the universe is stranger than expected, but not beyond understanding. That is enough for tonight. Good night.